Ethan Isaac. Daddy Hall Sajak.
Hi, I'm Miss Hall.
Hi, I'm Ethan Isaac.
Hi, I'm Mr. Sajak.
And this is lesson 41, inverses of functions. Can you say that?
Inverses of function. Inverses of function.
All right, so this is example 2 from section 5.6, finding the inverse of a linear function. So first we need to show you how to find the inverse.
Okay. And finding the inverse, I always think of as kind of 3 steps. Number 1, I write the original in terms of y and x. Okay, number 2, I switch y and x. So now this would become x equals 3y minus 1. And the third step, why did you say inverse there?
Because this is the point where we changed to the inverse.
Oh, so the blue one is the original, the orange one is the inverse, and typically we write the inverse in terms of y as well. So now we need to isolate y. So add 1 to both sides, and then divide both sides by 3.
Do you show this step, dividing by 3 on both sides?
Yes. So that is how you find the inverse. I would also like to rewrite these in terms of function notation. So the original function, you want to keep it in blue, is f of x, just highlight it, equals 3x minus 1. And the inverse of f of x equals x plus 1 over 3. The Regents loves to use this terminology, f, you're going to yell at me, to the negative first power.
Oh, no.
That's what it looks like.
That's not how you read that.
But it's the inverse of f of x.
Okay,
Or
you
how
could
would
say
you-
it that way. You can say f inverse of x, the inverse of f of x, or f of x inverse.
Okay. So there are special properties now that these are inverse functions, right? You've learned inverse operations before. Now let's look at inverse functions. Let's look at the table of f of x.
So I'll do f of x in blue.
Okay, so x and f of x, and let's do 0, 2, and 4. Thank
Are those
you.
correct?
I just assumed. Yes, looks good.
All right, so I'm going to plot those on the graph.
It's 10 high, so you go 1 above.
All right, and this is a linear function, so we could have done this with 2 points. And
F of x.
yeah, we'll make sure to label our graph so we don't lose points on a Regents exam.
F of x is not enough?
I
think it would be.
It would be enough, but I would always, just to be clear, write the function just in case there's a g of x or, you know.
Okay, so now we're going to write a table of values. And we're going to pick the x's to be -1, 5, and 11.
Why?
Well, you're going to notice something special when
Oh.
we put in -1, 5, and 11. So -1.
-1, that gives us 0, and I substitute it in for this x. I substitute in 5, we get 2, and when I substitute in 11, we get 4. All right, so -1, 0 is here. 5, comma 2 is here. And 11, comma 4 is right off the graph, so right around there. We could have done this one with 2 points. It's a linear function.
And so what I want you to notice about these 2 tables is that the x and y values are flipped. Right? In f of x, you have an ordered pair 0, -1. And in the inverse of f of x, you have -1, comma 0.
So you're saying all we've done is we switched the x and y values.
Right.
Okay.
So what you could do, what you could be asked is, I could give you a table of values and have you graph the inverse function.
So you could be given these values of x and f of x, and then you'd have to produce the inverse table or just graph it and plot it on a...
Right.
Okay.
Is there anything else that... Oh, I want to know...
Reflection.
Yeah. that a function and its inverse are a reflection over y equals x.
So
it's really hard to see.
Yeah, I'm gonna connect
You
them.
like dot it. Okay, so every function and its inverse is a reflection over y equals x.
So I'm going to show you one point here that just, it goes in, so it goes in 3 and then it comes out 3. So this point is mapped to this point here, and we can even write the coordinates. This point on f of x was 2, 5, and it gets mapped to 5, 2.
Okay,
And we could do that for every point, yeah.
Can I write, so in essence, when you have to find the inverse, you're going to do it a lot for equations during class. But one, you flip x and y. And then the second thing is you solve for y.
And then you found the inverse. I would add a third step, which is to rewrite
In
y
function notation.
as f inverse of x. Because you want to be very clear that this is a different function that you found. Here's example 6, verifying that functions are inverses. Verify that f of x equals 3x minus 1, which is the function we just worked with, and g of x equals x plus 1 over 3 are inverse functions. Well, we already showed you how to get the inverse function. We now need to prove that these are inverse functions. And the way that you prove that two functions are inverses is you check that f of g of x has to equal g of f of x and that has to equal x. All right, so we need to evaluate all three of these things.
Can I pause right there?
In case you are unfamiliar with what f of g of x means, this is a composition of functions, and it might have been a while since you've done this, but f of g of x, that first term there, or the left side of the equals, that means that we're going to substitute what g of x is, which is x plus 1 over 3. What are you doing? I would never have thought of it like that. But we're going to substitute what g of x is into x in the function of f of x. So g of x is x plus 1 over 3, and you can see that we're substituting that in and applying that to the rule of f of x, because the way I like to say this to my students is, well, what's f of apples? Well, that would mean you'd substitute in apples to where x is. So now we're going to go ahead and evaluate that. Miss Hall really likes that. All right, and we get x, which is good. That's what it's supposed to equal. Let's go ahead and do the same thing for g of f of x.
So I first write the function g, leaving space for the input.
Right, the input is f of x.
The input is f of x.
Which is 3x minus 1. So now, since the fraction bar is a grouping symbol, we'll simplify the numerator. We'll get 3x over 3. And that's equal to x.
And I needed to prove both of those, right? I couldn't just do one.
Right, you can't just do one. You have to show both. Can you throw some equals between your step 2 and step 3? Yeah. And we have just proved that those two functions are inverses.
So what I was going to think about is if you had two function machines, and one is f of x and one is f inverse of x. So whatever you put in, I don't want to say it's x, but I can't think of one to do. Like, say it's 5, and I do something to it.
So when you do f of 5, you get an output.
And my output is 10.
Mm-hmm.
And then when I put it in here, right, because the ordered pair here is 5, 10. And then if I'm putting 10 in, and this is really an inverse, then the ordered pair should be 10, 5, and out should come 5.
Right, which is the x that you started with.
Right.
Right, because f and f inverse, it's like multiplying and then dividing. Those are inverse functions.
Operations.
Inverse operations, right? We get back what we started with. So in the case of f of g of x, we should get back what we started with, which was x, which we just showed that we did. And that only happens if the functions are inverses for both f of g of x and g of f of x.
Okay, so that's just my thought bubble of how I try to remember f of g of x and g of f of x, that they undo each other.
And this little thought bubble is pointing down to our picture?
Mm-hmm.
Okay.
Okay, so this appeared on the June 2016 Regents exam. Given f inverse of x is equal to negative 3x plus 2, which equation represents f of x? So I'm going to rewrite the inverse equation with y equals. Then I'm going to swap the x and the y in orange.
Oops.
And solve for y. So subtract 2 from both sides. And then multiply both sides by negative 4/3. Let's actually distribute that. Okay, so it's going to be negative 4/3 x plus 8/3 equals y, which is number 2.